Hi everyone, and welcome to our continuation of our overview and introduction to new features of OpenMP version 6, which was released in November last year, so November 2024. This is part 2, and this one will focus on and cover the new accelerator features. That means GPU or in general offload programming. And this is the agenda that we have prepared. Again, very quickly, we will review who is Michael and who am I. And again, we will review the OpenMP for accelerator fundamental concepts like what is offloading, what is the target region. I will promise to be brief on this. And then we will dive into OpenMP accelerator extensions, first covering OpenMP version 5.x with remark on what's being even better in OpenMP 6. Michael will cover the loop construct, array syntax to some extent. We will look at the error and actually in more detail the requires directive, which are both again in the context of GPU programming. And then what is really important, unified memory. Yeah? That means exploiting the modern features, the features of modern GPUs. I will quickly talk about memory management and what is new. And then, depending on how much time is left, Michael will talk about how OpenMP enables the interoperability between OpenMP itself and HIP or CUDA, yeah, the GPU programming models of the two vendors. And if time permits, we will also look at more advanced asynchronous GPU programming topics. So who is Michael? Yeah, he comes from both OpenMP and AMD. So at AMD, he's a principal member of the technical staff. He's working in HPC for quite a while. I think I know him since 2006, maybe 2005. I hope I said the same in the previous webinar. We can check later. And at AMD, he's working on the Fortran compiler. So he really knows how OpenMP is compiled, not only for Fortran, also for C and C++. In the OpenMP context, he's a language committee member since about 2009. He's not only active in the accelerator stuff, but also on other topics. And finally, he's a CEO of the OpenMP ARB, that's the Architecture Review Board, basically the organization that owns the OpenMP specification. And he's making sure that we are making progress.
Thank you for those accolades. So, and let me introduce Christian. So he's working as a senior scientist at Aachen University, and he's actually leading the HPC group there. So he's managing the whole HPC team that does user engagement as well as research. And one of the big topics that his group is working on is actually parallel programming and performance. And this way is where his contributions come in the OpenMP ARB, because since I know Christian, and if we slightly deviate between this introduction and the last one, let's just call it a senior moment. So they had countless contributions as a group, and also Christian personally, to the OpenMP language. And since a few years, Christian is actually leading the Affinity Subcommittee, which takes care of mapping computation such that it's close to the data, or bringing data closer to the computation in terms of OpenMP features. And then he also wrote a book. It's called Using OpenMP, The Next Step, published by MIT Press. It's a very good book. If you don't have a copy of it, you should definitely get it. I read many chapters of it, and I really like the way they present OpenMP. So if you're interested in having a resource outside of the OpenMP specification to see how OpenMP works, this is going to be a great book. All right, yes. Back to you.
Thank you, Michael. And we are working on a new version of the book. Yeah? So Michael is part of the team. And so we are doing these webinars on different topics together since quite a while. So we share the parallel programming or language committee background, and Michael brings in, as I said, compiler expertise. I might be a little bit more on the user side. And if you watch those webinars over time, I guess you can see that we are becoming more senior. Yeah? Well, let's see review of OpenMP for accelerators. So OpenMP version 4.0 in 2008 introduced the principal support for accelerators. Back then, coprocessors were still a thing. It continues to have the traditional model. That means the computation starts on the host with an initial thread joined by worker threads to form the team of threads and so forth. But it was extended with a device model so that the host, depicted here, can offload to one or more devices. These are typically nowadays of the same kind. That means the control flow can jump from the host to one or more devices. And then the fundamental idea is that you can use the same and additional OpenMP constructs, directives, and clauses and API routines to actually make use of those devices. So OpenMP continues to support host-centric programming. That was the topic of our previous webinar, where we covered what has been added in OpenMP for this, traditional multi-core and many-core CPUs, heterogeneous memory, and so forth. And today we are going to look at these beasts over there. So very quickly, we start on the host. This is a left grayish box here, and we have some memory. Let's call it the variable, an array or a matrix A with some address here and also some data. And this is a device that typically comes with its own memory, be it shared or not. And the idea of OpenMP is that we have so-called offload regions marked by the target construct. You will see that in a second. And then we get all those things that you know from OpenMP, like the data environment. That means shared data and private data and so forth. You continue to have it on the host, and you will get it on the device as well. And that means if we have the OMP target here, we can actually make use of the so-called map clauses that contain a, let me call it that direction to actually manage the data environment on the device. So we can allocate new data there, another array A, or we can map data from the host to the device. That means in this particular image, copy data from the host to the device. Later on, Michael will talk about unified memory. So it's not always a copying. Let me spoil that so far. We can execute compute kernels on the device, probably then doing something with the data. And at the end of such an offload region, we can map data back from the device to the host as illustrated, so we can collect returns. And we can combine this with to from. We can have data regions that span the lifetime of multiple accelerator kernels and so far. So this review is meant to actually make sure that we are all on the same wording. And at the end of this kernel here, the data environment on the device is being destroyed, meaning all data is being removed. So let me emphasize this. The idea is that OpenMP separates offload, this is the managing of the data environment, starting the kernel and expressing parallelism. So we need as programmers explicitly some constructs, some constructs to make sure that we are using all those GPU cores that are available on the device. Let me illustrate that with a very simple Saxby kernel. So we're doing this well-known operation, y equals a times x plus y, and the target performs the offloading as shown before. Mapping x to the device means we get x on the device. Mapping to from of y means we get y on the device before the kernel and the result back. And on the device, we need OpenMP constructs to actually express the parallelism. Depending on the device type, parallel 4 with or without a SIMD could be suitable, but it turned out in the past that the semantics that came with OpenMP 1 and 2 meant for multi-cores, with multi referring to not too many cores actually, were too strict to support those devices really well. And Michael will cover the loop construct for exactly this reason later on. So GPUs, if you looked at them, are multi-level devices. We have thread blocks, we have individual threads, and they are most efficient if executing SIMD constructs. So instead of the parallel 4 with or without the SIMD, we need something in OpenMP, or we needed something in OpenMP to actually express parallelism in a hierarchical way. So we call this teams. That means we have multiple OpenMP parallel regions executing inner loops with threads, meaning multiple individual OpenMP teams, and then possibly also using SIMD units. And this is what has been introduced with OpenMP version 4 and extended with support for SIMD later, I believe, with OpenMP version 4.5. So teams starts multiple teams distributing on the first, meaning outer blocked level, this loop over the teams. Parallel 4 actually starts all those teams in the with the semantics of the parallel region in the 4 work sharing construct that you're aware of, and then possibly also apply SIMD so that we have up to these 3 levels of parallelism. That's good in order to exploit the hierarchical memory hierarchy. That's not perfect in terms of relaxed synchronization semantics, as I indicated before, and Michael will cover the possible replacement or extensions of this approach with loops a little bit later on into the talk. So I hope we are all more or less on the same page here in terms of wording and terminology. So what has been recently added with OpenMP 5.x, meaning x equals 1 or 2, and refinements made in OpenMP 6. One was the extension of, I hope this translation is correct, jagged arrays. So that means if we have an array, which is a pointer consisting of a pointer, 2 pointers, where we have, for the sake of simplicity here, 3 rows or of a varying row length. So that means at the end of the day, we have a non-rectangular memory space that we intend to map to the array. This has recently been made possible in OpenMP. So this is a declaration of the array. Let's omit the allocation, the initialization, and so forth. If we want to map such an array to the device, we can map the initial pointer and then the sequence of pointers that this initial array consists of. So the important aspect here is that we have an, let me call it what's the terminology here? So in OpenMP, we have a language extension. So that means we can express something that's not part of the C and C++, or maybe even Fortran base language, so that the compiler can generate corresponding mapping code. And you have seen maybe similar extensions before when we had array slicing and array sectioning support, both in the accelerator programming, but also in expressing task dependencies. So with this kind of 2-step mapping, we can map jagged arrays. What's, I think, more intuitive, and at least for my applications, more important, is that we have user-defined mappers. So maybe declare reduction, which was a support for user-defined reductions. Now we can also declare a mapper. That means we can define how the OpenMP runtime maps our own data structures from the host to the device, and possibly also from the device back to the host. And in doing so, we can optimize the data movement. We can respect the access patterns that are important for our application, and so forth. So let's take a look at this here. This is a my vector that consists of the length information and the actual data. Let me call this the payload, and some meta data resulting in the data type of this, of this name, and being instantiated here. And for the sake of an example, I declared 2 different mappers here, the vector vecpos and the vecvel. So that means this is the name of the mapper. This is a data type of the mapper, and then placeholder variable. And this is then actually what's being mapped. Here we have the position and the data. And this is how it's being used. So if we have an OMP target region, we can specify our own mapper on this particular variable. And now I'm introducing a variable that I didn't use before. Sorry for that. Yeah. I missed the declaration in my example here. But then we can make use of this variable s with a do something with s. So declaring our own mapper allows us to map our own complex data structures, respect access pattern, even if we have a dense data structure, and so forth. And with that, I hand over to Michael, and I'm the clicker, so that means if Michael says something, I will advance the slides.
All right, thank you. So one of the things that I would like to talk about is how you can spell the device loops a little easier with less typing. So this is what Christian has shown you with teams distribute parallel for or parallel do if you're a Fortran programmer. And we recognize that this is a lot to type and does not really convey the full meaning that you probably want to convey to the compiler, which is this loop is parallel and bring it over to the GPU. The bring over part, that's handled with target, of course, but then all this handling with teams distribute parallel do and so forth, that seems to be extra typing for no good reason if you just want to express, that there's a loop that should run on the GPU. Click, please. Now with OpenMP actually 5.0, and we did a whole bunch of refinements in 5.1, 5.2, and also 6.0. You can now write target teams loop, or in the latest spelling in OpenMP 6, you can just write target loop. So it's even another 5 characters or 6 characters if you consider blanks. Shorter and actually conveys the meaning. So to the compiler, this now means go to the GPU, in this case, or the accelerator in more general, and run the following loop in parallel and do all the optimizations that you can figure out. And use SIMD units if they are available, use the available wavefronts or warps or whatever the underlying architecture uses, and just bring over that loop in the best possible way that you can figure out. If the compiler doesn't do what you want, of course, you can go back to the previous spelling and be more explicit in terms of, how many teams you want, what the thread limit should be, and how the specific mapping should be. And, if we were going a little deeper than we can today, you would also find that, the loop construct has additional clauses that can specify, the level of parallelism that the loop construct should be binding to. So you can make it behave like the distribute that Christian was explaining before, where the loop is distributed across a number of teams. You can make it behave as like a parallel do work sharing construct, or you can make it behave more like a SIMD construct. And so you can even use that loop construct to, provide the right level of optimizations as a first step before you go to the more explicit forms. Click, please. The other thing that we did in OpenMP 6, and that's not necessarily to do with loops, because in this example I'm actually removing the loops. So as the Fortran programmers on this webinar are aware, Fortran since ages has array syntax. So the Saxby example that we use throughout today's webinar usually uses the explicit do loops or for loops, but in Fortran you can also write it as an array statement where you just express the formula to be y equals a times x plus y. So the actual mathematical definition of the routine, and then click. The usual way to bring this over to the GPU would be to basically undo the array notations and make the implicitly contained loops explicit, like we've been showing before. And Christian, when you click once more, one of the additions that we did with OpenMP 6 was introducing a special construct called workdistribute. If you are an OpenMP programmer, especially in the Fortran space. You may remember the work share construct that OpenMP offers since probably 97. I think it was they are pretty early on in the OpenMP spec, where array notations are sort of auto-parallelized by the compiler, and work distribute basically resembles the same idea and bring that over to the accelerator or GPU space. So what OpenMP would do for you is it would parallelize the implicitly contained loops in the array statements and bring them over as kernels to the GPU. It will do so respecting the Fortran base language semantics, so dependencies and the effects of Fortran array notation will be carried out as usual as in regular Fortran. So this is a nice way to, get those kernels over to the GPU without being explicit in the loops. Click, please. And then the other thing that we added is, especially for discrete GPUs with discrete memory, it was always a bit cumbersome to deal with Fortran allocatable entities. So in this case, the data array of this dummy module, where the first thing you had to do, because it has a safe attribute and it's a module variable, you have to OpenMP declare target that entity so that there is a version of that thing over on the GPU. And then when you did the allocate and deallocate statements, you would have to have explicit target ender data and target exit data constructs for the allocation to also happen on the target device and potentially move data around, or before you do the deallocate, have the corresponding target exit data that removes the allocation on the GPU. Now, in this example, it's really easy to see where you have to put these things, but then allocation and deallocation can also happen as part of Fortran intrinsic assignment, and that means you don't get to see all those allocations and deallocations. And so in OpenMP 6, we introduced what we call automap. So you can prefix a data entity with automap colon. You can cross out all the target ender data and exit data construct. Click, please. And what it does is, if you have an allocate statement, the underlying OpenMP implementation is supposed to allocate an object in GPU memory. If you do the corresponding deallocate, it's going to do the deallocation in the GPU memory. And this also works for all the implicit allocation and deallocations that may happen in Fortran. Click once more. The restriction is that it only works for variables with safe attributes. So in this case, module scope variables that have the implicit safe attribute. I like to be explicit about this, so I put it there. And the declared target directive that you see on the screen must be visible at the allocation and deallocation site, so that the compiler can actually introduce the corresponding mapping statements. All right, back to you, Christian.
Sure. Yeah. So as good programmers, we all try to avoid errors, but sometimes the implementations, the devices, and so forth make some errors. So to some extent, we can deal with them. But first, let's look at what we can require. So the require directive is relatively new in OpenMP, and the fundamental idea is that you can express some dependencies on specific features that come with the OpenMP implementation, which consists of the compiler and the runtime, and or the actual hardware. So it could be that your implementation supports something, but you're using a hardware that does not support this, and so forth. And on the following slides, I'm going to list what you can actually require. So you can say pragma-OP requires unified shared memory. So with a brief example or explanation, and then I'll summarize some possible use cases. And as Michael already answered in the chat, OpenMP 6 implementations, or full OpenMP 6 implementations, are not available. So it means use cases will also evolve over time. So unified shared memory, I teased that before, will be a separate chapter here. Michael explains more about that, but the fundamental idea is that if you USM, Unified Shared Memory, implies that the host and the device memory spaces are logically unified or logically one. That means it's not necessary to copy data from the host to the device. So if you write pragma-OMP requires unified shared memory, your implementation will generate code that assumes that host or that assumes and exploits that host and device memory spaces are logically unified. That means the target teams distribute parallel 4 explained before will generate a parallel kernel on a device, and then this data structure actually has to be accessible, not necessarily present, but accessible from the device. So there's no map in here, so that means we need this unified memory in order for this code to work correctly. So this is what you specify with OMP requires, kind of like an assertion from a programmer's point of view. The next one is reverse offload. When I first thought about this concept, I thought this to be strange, but actually it makes a lot of sense. So if you have a host directive model, but still want to exploit the performance and scalability of modern systems, you have to offload as much as possible. That means to compute on the device as much as possible. But there are certain tasks that you actually have to or could better do from the host or any other device. And this is what reverse offload allows you. So that means from a GPU computation, you could do a target offload back to the host, for example, to do I/O. And if you want to ensure that your implementation supports that and also the target hardware, you can require reverse offload to be supported. So assuming you're on the device, you want to offload back to the host without ending the offload to the device. This is a reverse offload. Dynamic allocators. So we have some extended allocator functionality to some extent that will be covered not in the next, but in the chapter afterwards. So this requires and ensures, so if you specify this requirement, it ensures that the code region can actually make use of dynamic memory allocators within the target region. Not only on the host, but specifically on the target region. pragma-OMP requires dynamic allocators is applied to the following code region, which is this target. And here we're doing a OMP target alloc of a certain size on a certain or on the default device. Atomic default memory order, and then you can specify one of relaxed, acquire, release, or sequential consistency as a memory order. Means or as an application to the OpenMP atomics. I believe we covered them in the previous webinar or maybe in the one before, also in this context of POP. So that requires that the atomics have a certain memory order, namely the one that you specified in the corresponding scope. That means, or you can assume that it kind of sets this as a default. Then device functions implicit declaration. So this requires the OpenMP implementation to ensure that functions called within the target region will get a target implementation as by default. So that typically you have to declare your own user code functions as a target function if you want both versions to be compiled, meaning one for the host and for the device. And with that, you can eliminate these declarations and ensure that require that the implementation does that automatically. Self-map is a feature of unified shared memory. So if you require self-map, that implies unified shared memory, and that indicates that unified shared memory works so that the mapped storage, meaning the device storage, is the same as the original storage. So that you do not have to do any mapping, be it explicit or implicit. It's actually the same logical memory. So that gives you the guarantee that no copy is being made. So in general, and in addition to the brief examples that I tried to give, what can you do with this? Of course, with the requires directive, you can improve portability. So what do I mean with that? If you specifically rely on a certain OpenMP feature to be present and supported, this is kind of a flag to some extent for the implementation, to some at compile time, to some extent for the implementation at runtime, to ensure that your program behaves as expected. But it's also useful to actually discover during the compile time, I said, that if a certain feature is present, and also to document the assumptions of your code. So if you assume that at some point all devices support unified shared memory, for example, you can still put this as a required in order to document your code for you, meaning for your future self. Speaking of my own experience here, but also for others working with your code and reading it and maybe compiling it on other architectures. And finally, to some extent, early error detection. So if you expect a certain functionality to be present, with that you can make it explicit, as I said before, to the OpenMP implementation already at the compile stage. That means you get an error message if you want to compile the code for a target architecture or with a target implementation that does not support your requirements, and that's probably much better than dealing with runtime errors later on. And maybe, so it's my hope, not speaking for compiler vendors here, at some point implementation may eventually use the insight, the additional information that you specify with the require directive as a hint for optimization, meaning generating more efficient code under the assumption that your requirements hold. When this will happen, if this will happen, at least for me, that's hard to tell. Then let's take a look at the error directive. So with that, OpenMP wants you to provide, or wants you to give a mechanism to actually detect and handle errors within OpenMP parallel regions, to some extent for the host, to another extent on the device. So the error directive has in general two modes. It can either issue a warning, that means something is printed to the command line, or it can actually terminate your program. That means uses for critical, unrecoverable errors only. And you can specify this with a severity of either warning or being fatal. That means cancel your program. And of course, it contains, or you can also specify a condition. With that, again, working together with requires, you can enforce certain constraints, ensuring correct device selection, for example, or you can detect unsupported features. So I try to come up with meaningful examples. If you have more to share, we are happy to see them. In particular, the OpenMP example effort would profit from that. So if OMP get none devices return 0, that means the implementation is not able to detect supported devices at the time the program is running, or if those devices are not available by whatever mechanism in your environment, resource manager, or operating system, you can specify an error message that no GPU device is available and stop the program execution. Probably, or in some cases, better than seeing the error message of the runtime. Or you can make use of it for debugging. So here we have a target data map, a target data region, sorry, with a map from the device to the host, mapping this device. And if here you're making use of OpenMP API routines, if the this presence check fails, then the device memory allocation failed is probably a better error message than something like a segmentation fault or something like that. Of course, you can extend that with your own variables, information about locations in the program, and so forth. And I believe with that, I hand over to Michael for the anticipated unified shared memory discussion.
Yes, and Christian already introduced one core component of this, the requires directive. So I'm going to dig a little deeper than what he was showing before and explain why you specifically need this for GPUs with USM support. Please click. So if you go back to Saxby, today we have GPUs where the host and GPU can share the same address space. So that's a very generic concept. And then there's like a bunch of ways how you can make this work, either via, say, something like a software emulation where you use page migration to move a page from host memory to GPU memory, let the GPU work on that page, and then when the host wants the page back to access it, you can ship it back. That requires, like in the Linux kernel, there's a feature called HMM, heterogeneous memory migration. And so several of the GPUs can use that infrastructure to move memory around via those page migration mechanisms and basically emulate the concept of a unified shared memory and the same address space idea in terms of software. And then, of course, there's like two or many other ways how you can also do this in hardware. So one notable thing is via a memory coherency protocol on a fast memory link. Think of this as being something like NVLink or Infinity Fabric for AMD GPUs, where there's this coherency link between the GPU memory and the CPU memory. And so despite that you still have discrete memories, the underlying memory coherency protocol does on some granularity, the transfer, and the hardware is handling the back and forth of those memory locations. And then, of course, there's the way to actually have shared physical memory. So the AMD Instinct MI300A is one of those examples where there is one single big block of high bandwidth memory. And then the GPU portion and the CPU portion, they basically share the same physical memory pages. Now, if you have a code like this that I'm showing here on the screen, click please. And Christian was showing something along those lines when he introduced requires. If you just cross out the map clauses, because apparently you don't need them, they don't do any particular memory transfer anymore, you would think that's all you need to do, right? And the requires clause that Christian was introducing is actually not needed. Now, the funny thing, please click, is that when you do this, so basically you just strip out your map clauses and you think you're done, the compiler will actually put them back. Because it's a requirement by OpenMP that when you have a target offloaded region that uses data that the compiler needs to figure out what are the variables that are being used inside that kernel region, and it will actually have to reintroduce the map clauses that you just removed from your code. Some compilers can actually look at those map clauses and try to elide them. So for instance, LLVM has a feature in the underlying OpenMP runtime to detect USM mode. And if it does so at runtime, the effect of those map clauses is elided, but they are still there, right? And they still do some reference counting and some other bookkeeping under the hood. So they're not completely gone. It's just that the memory transfer effect is elided. But the semantics of the map clauses are still sort of there. And then other compilers, for instance, the next-gen Fortran compiler at AMD, they have special compiler switches where you can say, don't do map clauses. I know I want to run on unified shared memory. And then they can elide those map clauses statically at compile time. Like if you didn't write them, they are not being added back, or if you have them in the code, they can be elided with the corresponding loss of semantics when they are removed. Click, please. And so, this is where OpenMP requires unified shared memory comes in. So now when you write this requirement, you basically document, like Christian already has indicated, that your code makes certain assumptions. And in this case, the assumption is that it's running on unified shared memory architectures. So you didn't put map clauses, and the requires now serves two purposes. First, it documents this assumption by you for your code by not implicitly adding the map clauses. And secondly, if you have an implementation or if you want to run that code on a machine that doesn't have unified shared memory, it is an error condition that is detectable at runtime, and the compiler can give you information about that it doesn't support that mode of operation, or at runtime, the runtime system of OpenMP can give you that information that you're trying to run something that is not actually supported by the underlying hardware. With that, Christian, back to you.
Thank you, Michael. Yes, and let's talk about memory management. So some slides or some parts of the slides also focus on stuff, talk about stuff previously available in OpenMP or targeted toward the host. So I will focus on what's new in OpenMP 6 and to some extent also for devices only. Let's review what's an allocator, coming from C++. The definition in OpenMP is that an allocator is an OpenMP object that fulfills requests to allocate and deallocate storage for program variables. So the idea is that in OpenMP, we can use predefined allocators or define our own allocators, which both are then of OMP allocator handle T, so that we can influence how memory is being allocated and deallocated. So we can select the kind of memory, we can specify additional properties in forms of traits and so forth. This has been introduced with OpenMP version 5 with the goal, and actually we achieve this goal, to make constant improvements in every update, giving us a general concept that is suitable to target the recent developments of systems and architectures. These are the predefined memories that enable us to select a certain kind of memory, like the large capacity memory or the high bandwidth memory, and so forth. And the idea is that the OpenMP runtime maps our kind of abstract requirement to actual physical memory, or let's call it a certain kind of memory that is present in the system when your program is being executed. So we can specify allocators with so-called traits with the so-called OMP init allocator function. We specify a memory space, selecting one of the memory kinds, and a set of so-called traits. And on the following slides, I'm going to talk about exactly these traits, which have been expanded, hence this kind of lengthy introduction. If we do not need that, we get defaults. Otherwise, we can make use of this function or routine to actually create our own allocator, use it with the OMP alloc routine as an argument, or set it as an OMP default allocator for the OMP alloc and OMP free routines. This is a set of allocator traits, and there are three different allocators that I would like to highlight here. First, a brief example on the partition size, and then partitioner and partitioner arguments. These have been introduced with OpenMP 6. Apart from that, we can ask for certain alignment. We can specify a fallback. What happens if an allocation fails? Return null, abort, use a different allocator, or just use a default memory. We can ask for pinned memory, which is very important if we care about performance in the offload in some use cases, and so forth. The idea of the partition trait in conjunction with the part size as a partition size was to extend the support for non-uniform memory architectures in OpenMP, so that we can either ask the environment to perform actually distribute the physical pages that are behind the logical memory allocation initialization, So we can ask the environment to do that, meaning the operating system, use the nearest memory, or use some kind of blocking and interleaving. So I said this already. Yeah. This is also what I already talked about. So what's new is that I will show on the following slide how interleaving can be used, and then later on I will talk about the partitioner. So let's take a look at this interleaving. So these are it's a simple routine, a data structure, sorry, to contain the traits. We ask for a partitioning to be done by the allocator with the interleaved setting, and we want the partition size to be 1 megabyte. And then we can initialize the allocator with a selected memory space. In this simple example, it's a default memory, typically the DDR memory, yeah, and specify 2 traits. Yeah, so there's an empty space missing here, sorry for that. And then allocate a data structure named A. And in my example, this data structure is 6 megabyte in size. So what will happen here? First, let me add, in the first release, OpenMP 5, with interleaved support, we forgot the partition size, so it was kind of undefined, or in the best case, defined by the implementation, how large the actual partition would be. Now you can specify that, and interleaving applies a so-called round-robin distribution. So if we have 4 physical partitions of the memory, that's what I'm trying to illustrate here. The first megabyte will be physically allocated on the first memory partition, the second going here, the third going there, the fourth going here, the fifth again, yeah, round robin going on the first memory partition, and the sixth would go there. Yeah. So it's the distribution of 6 megabyte as I just tried to illustrate here. That's good, but maybe that's not perfect. Yeah? So if you invest a lot of effort in order to balance the work, meaning the computational load in your program, and if you also want to have full control about how memory will be allocated and then physically mapped, OpenMP now supports more fine-grained control about that. Unfortunately, there's no implementation available for that at this point in time, so I don't have a working example, but I want to briefly illustrate the idea here. So the partitioner is a new concept in OpenMP, namely a memory partitioner, and in the allocator traits, you would specify a handle to a certain partitioner. So that's again an object that's defined and constructed and initialized within the user code, and then it takes a certain argument. So let me explain that. So we specify the partitioner here, which allows you to define memory paths and distribution across the storage in your own way, exactly by the means of a memory partitioner. So it's an opaque object to some extent that computes a set of computes the memory partition as a set of so-called memory paths, where memory part is then a storage block in a single storage resource, meaning a physical allocation like a page or something specific if you're on a different or special system. And the idea is that the memory partition is being computed by a code in your program. So we have the OMP init mem partitioner routine that creates such a memory partitioner that can be used with an OpenMP allocator, as explained before. And it takes one argument that's important, namely the compute proc, which is a routine as an argument that determines the number of memory parts and their distribution across the storage resources by making use of the corresponding arguments. And there are further routines. I didn't introduce them because I wasn't able to compile a working or to create a compilable example here, but you have to also clean up memory partitioners at the end and so forth. So we're skipping over that in this introduction. And finally, what has also been added to OpenMP 6 is a set of memory space retrieving routines So that means via the API, you can query the memory spaces, meaning kinds of memories available on different available on which devices they are available, and so forth. So for that, we recommend you to take a look into the OpenMP cheat sheet, yeah, our quick, not so quick anymore, syntax reference cards. With that, I hand over to Michael again for the final main topic. I'll take a look into the chat.
All right. So interoperability between OpenMP and HIP and or CUDA and maybe even OpenCL if OpenCL is a thing for you. But I will restrict myself to those two. Click, please. So, the idea of this is that we have a bunch of kernels like compute 1, compute 3, that are running inside a data environment. And then we have the Saxby kernel that is supposed to do a Saxby operation. Think of this as like being very cut down mock-up of something like conjugate gradient methods, where you have like multiple kernels that are running in succession to implement one step in the conjugate gradient method. Click, please. And so, with the outside target data environment where X and Y have been mapped, we've been briefly touching on this, that this is possible, and now you got an example on screen. Then the Saxby kernel basically is the traditional for loop that we've been showing a bunch of times already, and then target teams distribute parallel for or target teams loop if you want to use the shorter version of it. And then inside that kernel, we don't use any map clauses. The compiler will add implicit map clauses that basically determine that X and Y are already available as part of the data environment, and so it will not retransfer this. All right, click, please. Now let's suppose that for a second that the compiler doesn't do the right job for this kernel, and that you want to rewrite that kernel in a lower level language like HIP to get additional performance out of the GPU. And let me say that this is a contrived example, so any decent GPU compiler will produce the same code regardless of whether you use HIP or OpenMP. But I think as like a smaller example to convey the point, that's still useful. Of course, you would probably try this with larger kernels where there's more potential for you to get additional performance out of HIP. All right, click, please. All right, so here's a HIP version of the Saxby kernel. Actually, it's not so much a HIP version, it's actually also a CUDA version, because in that regard, HIP and CUDA are bitwise identical. So the way this works is the Saxby kernel has this thread IDX block dim specifiers to basically determine where in the computational grid of the kernel the next couple of statements are going to happen. So this gives us the coordinates in terms of a flattened one-dimensional space instead of the original loop that we had. And then the HIP implementation, in this case, I'm simplifying a few things in that I'm asserting that the number of wavefronts and threads that I run on the GPU actually evenly divide the number of array elements that are being processed. And then, there's the triple chevron syntax to actually invoke the kernel on the target device. So far, standard HIP programming, and nothing really fancy about this. Now, the thing is, click please, that X and Y are now device pointers. So the way you invoke the Saxby kernel are the actual device pointers that are pointing to the memory location of X and Y in the GPU. So something that you would get from CUDA malloc or HIP malloc. So really something that has no meaning on the host. OpenMP, on the other hand, if you wrote OpenMP kernels before, and what we've been showing is that inside the kernel, you actually deal with sort of the host entities that are auto-translated like Christian was showing on his third slide, where OpenMP does some magic under the hood to actually translate things for you and associate the host data with the device pointer or device data if copies have been made. Click, please. So now we need to tap into this, right? So what we need to understand or what we have to get out of the system to make a HIP kernel work is to get the actual device pointer. Click, please. And so when Christian was showing you the target construct with the map clauses, click. What happened was that, OpenMP under the hood somehow manages host memory and device memory, does the transfer where needed, and kind of maintains a mapping table, click please, that contains information that a certain host pointer, in this case the X array at ABCD, or address ABCD, has been mapped to a device pointer EF12. And anytime you refer to X in the kernel, OpenMP knows how to find the data. Click, please. And so what we need for the HIP kernel to work is actually this device pointer. So we need to ask OpenMP to return that device pointer and hand it out from the internal bookkeeping that it maintains for us. Click, please. And this is how it works. So there's the use device adder clause that you can use for this purpose. And so what happens is inside a target data construct, you can use that clause to basically tell OpenMP to look into the bookkeeping table of mappings and retrieve for a given host pointer, a given device pointer, and store it in the variable. The brain twister thing about this construct, though, is that the original pointer variable is hidden within the target data construct while the translation is active. So that means if you, like on this screen, have this type star X outside of the target data region, and then you have use device adder inside the curly braces of target data, the original X that was pointing to host memory is kind of hidden and shadowed by a new X that now contains the device pointer. That's a bit of a weirdness, but it also helps us, when you elide the OpenMP directives, to get something closer to this serial or non-GPU version of your code back. All right, click please. Now, what we can do is we can plug all this together. So, we do the allocations, we use the original code like I was showing on my lead-in slide with compute 1 and compute 3 being not modified at all. And then when we replace the original Saxby kernel written in OpenMP with the HIP version, or I should say the HIP trampoline that then uses the triple chevron syntax to actually invoke the kernel, I'm using a target data construct with use device adder for X and Y, and I'm indicating what the mapping table contains and what the actual X variable contains in here, so that when you look through after the webinar has taken place, you can see that outside the inner target data, the mapping table contains the proper mapping that I was explaining. And then inside the inner target data construct, the mapping table still contains the same data, but now X has been reset to be the second part, the actual device pointer. Click. And we're gonna skip this for the matter of time. So we will talk to Bernd to see if we have to have part 3 for this webinar series. So stay tuned. This is sort of a cliffhanger. And with that, Christian, please proceed to the last slide.
I'm working on that. So there's a final question. Maybe you can elaborate on that again. Can HIP and OpenMP be compiled in a single source code, for example, to make use of managing memory with HIP while using work sharing constructs with OpenMP offload?
No. That is something that we cannot do. This is a current limitation of the HIP compiler. It does not support full OpenMP at this point, and you cannot mix HIP and OpenMP in the same source file. So you would have to actually move the HIP kernel to a separate source file and compile it with the HIP-CC compiler. and then link everything together using the OpenMP compiler or the HIP compiler. That doesn't matter then at the linker stage. But right now we cannot have a single source file.
Okay.
All right. There was one more question in the chat that I was about to type into the chat window. Does the OpenMP alignment respect the alignment specified at compile time, e.g. -align array 64 byte in Intel Fortran? I think those two are somewhat orthogonal. So the -align, as far as I understand, Intel Fortran will just provide standard alignment for allocatable objects and maybe even stack arrays. So that's something I would have to read up in the doc. But basically, that's kind of the underlying base language alignment. And of course, that can inherit into OpenMP. And OpenMP, for instance, has the SIMD construct has an align clause where when you know that you were using the -align command line option, that everything is 64 byte aligned, you can use that to tell the compiler to produce slightly better code. What Christian was showing is actually on top of that, so that when you have a compiler that is not the Intel Fortran compiler and that may not have that feature, you can still get like a portable solution that gives you alignment, and you can ask for different alignment properties, like even page alignment or 2 megabyte alignment. These kind of things you can do with OpenMP that you may or may not be able to do with the underlying base language compiler already. And that's also why we introduced it to be portable in that aspect.
Okay, there was one more question, and it was pointed out in the chat again. Do we need to provide any additional flags for the OpenMP unified memory class, like in OpenACC, where we provide GPU equals managed when using NVHBC compiler? When using compilers such as Clang, Intel GNU compiler, or with OpenMP flag, handle it automatically?
Yes, I think there was a bit of a crossover because I tried to answer that in the chat. So let me reiterate that answer. So basically, from an OpenMP perspective, no, because basically requires unified shared memory. Just says your code needs the notion of this concept, and that you will not have map clauses in your code, and the code will not work on a system that does not have USM. Whether or not the underlying implementation needs more flags to make USM happen is an implementation thing. Yes. Especially the ones that have like are working on page migration may require to allocate the pages from a special pool to say ensure that the pages are pinned or that the data is properly aligned for page migration to actually work. And so this is more a question for the underlying implementation. And so that's something that's really is again orthogonal to what OpenMP requires in the code versus what the implementation has to do to actually make it work. So if you think AMD GPUs for a second, there is a special flag that you would have to set HSA_xnag equals 1 in the environment to put the GPU and the driver into unified shared memory mode, so that either page migration would kick in or the memory coherency protocol on the hardware level. So, there may be some environmental flags or settings that you would have to take to make USM work, but then OpenMP, on the other hand, just runs on top of what the implementation provides and picks up those concepts.
Yeah, so to summarize, consult the documentation of your implementation. It might have some interesting tricks, different OpenMP implementation, feature support, and so forth.
Okay, thank you. Any further questions? Like either quickly type them in or raise your hand and unmute and ask the question verbally. So, okay.
Okay.
Yeah, it looks like so. Thank you very much, Christian, Michael. It was a fun as always.
Our
Thanks
pleasure.
for joining us. There will be more Bob webinars. Watch our social media channel and our website for announcements. The next one will probably early April. So thanks everyone, and yeah, have a rest of a nice day and a nice week. Bye.
Thank you all.
Bye.
Bye.